Welcome back. We're going to look at a filter structure that has only a single multiplier and, well, a single non-trivial multiplier. We don't consider multiplication by -1 in general to be a real multiplier because it can be done by just changing the sign. No other substantial change is done. So this particular filter has a structure that we haven't seen before, and so we'll figure out how to analyze this today and what type of structure this may be. In order to do this, let's first look at all of these summing nodes that we have and define a signal name coming out of each one. So we'll call this one W1 of n. Here, this is W2. This isn't actually following a summing node. It's just going to be alpha times W1, as we'll see. Here we'll have W4 of n. And right here, after that summing node, we'll have W3 of n. So what's the best way to start? I would start a problem like this by giving myself a little bit of room and starting to write down every relationship that we know. We know that W1 of n is equal to W4 of n minus xn. W2 of n is just equal to alpha times W1. We probably could have skipped having the W2, but when we initially start putting values in, it's easier to be inclusive and eliminate things with careful algebra than to eyeball it. So W3, let's see, that's going to be W2 of n, coming down on that diagonal channel, plus xn. W4 is going to be W3 delayed, and our output would just be W2 plus W4. Okay, now we can go ahead and start to simplify things. I'm going to drop the sub n notation by, I guess, and when there's a delay, I'll just indicate that with a z to the minus 1. So we'll have the W2 is equal to alpha, let's see, times W1, which is W4 minus x. And W3 is pretty straightforward. It's W2 plus x, 2 plus x. Now we can do W4. That would be a delayed version of W3, which is z to the negative 1 W2 plus z to the negative 1 x. And we know that W2 is equal to alpha W4 minus x. So that gives us W4 equals z to the negative 1 alpha W4 minus z to the negative 1 alpha x plus z to the negative 1 x. Okay, now we're getting someplace. We have an expression for W4, and just to use the space well, I'll throw it over here, and we get W4 is equal to z to the negative 1 1 minus over 1 minus alpha z to the negative 1 times 1 minus alpha x. Now, as you recall, we need y is equal to w2 plus w4, and w2, unfortunately, is also a function of w4. So that's going to give us the following. Actually, I guess we're not ready to do that yet. Let's go back and find an expression for w2 first. w2 is equal to alpha times w4, and now that we have w4, it's going to be alpha times z to the negative 1, 1 minus alpha over 1 minus alpha z to the negative 1 times x minus x. Well, it always gets worse before it gets better. Let's see what this ends up looking like. So now we have alpha z to the negative 1 minus alpha squared z to the negative 1. That's most of the numerator. And then we'll have when we combine these terms here, 1 minus alpha z to the negative 1, and we'll multiply it by alpha, is going to give us alpha plus alpha squared z to the minus 1, and actually I neglected to take into account that negative. So now we have alpha z to the minus 1 minus alpha squared z to the negative 1, and then we have a plus alpha squared z to the negative 1, so those two cancel out. And so w2 is now going to be, oh, and I guess we can't forget the rest. There's an x out there, 1 minus alpha z to the minus 1 here. So this is going to give us alpha, let's put it out front here, times z to the negative 1 minus 1 over 1 minus alpha z to the negative 1 times x. So now I guess we're ready to combine our w2 and our w4 to give us a fraction that's all over 1 minus alpha z to the negative 1. We're going to have an x over here, and from w4 we have z to the minus 1 minus alpha z to the minus 1, and from w2 we have alpha z to the minus 1 minus alpha. Those two terms cancel, and now we finally have z to the negative 1 minus alpha over 1 minus alpha z to the negative 1 times x. Since we're writing this as our final conclusion, we can start being a little bit more inclusive about putting the x of z and the y of z in there, meaning that our h of z function is just this really cool thing. We've already seen this before though once. This is an all-pass filter. So the interesting thing about this is, sure, it uses a single multiply and we get an all-pass filter out of it. But in the light of what we've discussed about coefficient quantization, anything we did with this filter to quantize our alpha the alpha appears now effectively in the numerator and the denominator, so that the pole and the zero are going to be affected in exactly the same way, so that regardless of what a poor job we do with our alphas, we are guaranteed to have an all-pass filter.